Okay, so what I want to do now is review the Riemann integral a little bit. I'm not going to dwell on this too much. It's not super important for this course. Mainly, this is to motivate our definition of the Lebesgue integral. Um, It'll turn out that the definition of the Lebesgue integral is not that much different than a reformulation of the Riemann integral. Um, all right, so as we all remember, at the very least from Calc 1, if you haven't done the Riemann integral in like a basic analysis course, so remember the starting point of the Riemann integral are Riemann sums and partitions. So say I have a partition of A to B, which just means I have a sequence of points, x0 to xn, strictly increasing, and A is x0, xn is B. So if I have, let's say, a bounded function. So when we talk about the Riemann integral, we only deal with bounded functions. Okay? When you do, remember, when you do improper integrals, you take limits. But you're still, when you take limits, you're still integrating with respect to a bounded function. But anyway. Okay, so we can define the upper and lower Riemann sums in the usual familiar way. So they're just Riemann sums. They're sums of areas of rectangles with height little mi, height big Mi, and the width is just the width of each partition interval. And little mi and big Mi are just, well, if this function is continuous, it would be the minimum and maximum on my closed intervals corresponding to each partition interval. In general, these not need be continuous, so we do the next best thing, take the infimum of f of x on each interval and take the supremum of f of x on each interval. Okay, and yeah, this will give us a sum of area of a sum of area of rectangles that approximates the area under the curve, assuming f is nice and thus Riemann integrable, so area has meaning. Okay? So a typical picture for a nice function is as follows. For the lower Riemann sum, each term here, little mi times xi minus 1, is just this red area. Here's the height, the infimum of f of x on this interval. And this is the, the base, the width of each interval. Base times height, we get area. So we sum up over all these red rectangles, the areas. We get an approximation to the area under the curve that here graphically undershoots the area. And we do the same thing for the upper Riemann sums. Each term is of this form. This height here, the supremum of the function on each little interval, times the width of my little interval. And we add up the red areas, areas of each rectangle. We add that up. We get an approximation to the area that overshoots the actual area under the curve. Okay? And for graphical and discussion purposes, I'm just dealing with non-negative functions, so there's no issue with signed area. Okay? Again, I'm just trying to explain and motivate definitions here, essentially. Okay, so to motivate the definition of the Riemann integral and Riemann integrability, let's just look at this really nice function, 1 minus x, x plus 1, from -1 to 1. And let's see what happens to the lower and upper Riemann sums as the width of each partition interval gets smaller and smaller and smaller. Equivalently, the number of or I shouldn't say equivalently, but if the width of each partition interval gets smaller and smaller and smaller, that means the number of um, um, partition intervals, the number of rectangles gets larger and larger and larger. So you'll notice that if the width of each partition interval is not that small, then the upper sum is a pretty gross, it pretty grossly overshoots the area, the Riemann upper sum, and the Riemann lower sum pretty grossly undershoots the area under the curve. On the other hand, as the width size of each interval gets smaller and smaller and smaller, which means we have more and more and more rectangles, the Riemann upper sums decrease, and they start to approach a number that reasonably approximates the area under the curve. Okay. On the other hand, let's go back to 10. The lower sums, as the width of each little partition interval gets smaller and smaller and smaller, so we get more and more and more rectangles, the lower sums, the Riemann lower sums, increase and start to approach, again, what you could graphically consider a good approximation to the actual area under the curve. Okay, and you'll notice that these two actually aren't that different. This is the lower Riemann sum is 1.3132 here. The upper Riemann sum is 1.3532. And they don't differ too much to the actual area under the curve, 1.3333. Okay, so this motivates the following definition. So I'm going to define the lower Riemann integral of f on a to b to be the supremum of all these lower Riemann sums. And the upper Riemann integral of f from a to b is going to be the infimum of all these upper Riemann sums. Okay? And this makes sense to take the supremum and infimum. Remember, I mentioned that as we look at these lower Riemann sums and we get smaller and smaller and smaller partition interval sizes, the Riemann lower sums get larger and larger and larger and start to approach what should be the area under the curve. And the same thing here, as the width of each partition interval gets smaller and smaller and smaller, the Riemann upper sums get smaller and smaller and smaller, and they start to approach a number that is, should be what the area under the curve is. Okay. And in particular, as the partition, the size of each partition interval gets smaller and smaller and smaller, these two quantities should start to approach each other and approach what should be the area under the curve. Okay. So in fact, we will say that f is Riemann integrable if these two actually are equal. Okay. And basically, that's just saying graphically that we have the situation here that for really tiny partition interval sizes, the upper and the lower Riemann sums are virtually the same, and that common number is the area under the curve. All right. All right, so first let's prove that these actually exist, which is really fairly trivial, but and here we need to assume f is bounded. So let's assume f is bounded by some big M, positive M. So I can bound any lower Riemann sum. Remember, this is the infimum of f of x on xi minus 1 to xi. Clearly that infimum is less than or equal to m, because f is less than or equal to m. Actually should be less than strictly, but it's okay. Right, and so this here is just going to be equal to b minus a. It's just a telescoping sum. So the collection of all lower Riemann sums is bound above by m b minus a. And similarly, you can prove the collection of all upper Riemann sums is bounded below by minus m b minus a. So this set here is bounded above, this is bounded below, so these exist. Okay. And not that it's very important, but we really did just prove that we have these very crude bounds for the lower Riemann sum and the lower Riemann integral and the upper Riemann integral. A much more useful bound or inequality is that automatically, regardless of what f is, as long as it's bounded, the lower Riemann integral is always less than or equal to the upper Riemann integral. And graphically, that makes sense. You'll notice, if you haven't noticed already, that no matter what partition I take, the upper sum is always going to be bigger or equal to the lower sum. Okay? Or in other words, the lower sum is always going to be less than or equal to the upper sum for any two partitions. Okay? Which, I mean, makes sense. As the partition's interval size gets larger and larger and larger, this increases, starts to approach what should be the area under the curve. This decreases, so it only makes sense that every lower Riemann sum has to be less than or equal to every upper Riemann sum, no matter what two partitions we use. Or in other words, for any partition, any two partitions, the corresponding lower Riemann sum for one of the partitions is less than or equal to the upper Riemann sum for the other partition. Okay. Okay, and as I mentioned, we say f is Riemann integrable on A and B if these two are equal. And if they are equal, that's what reasonably should be considered the area under the curve. And I'm going to use, like the book, this R here to denote we're taking the Riemann integral rather than the Lebesgue integral. Okay. Okay, so an important technical note is that we can define lower and upper Riemann sums in a slightly modified way. In particular, I can define the lower Riemann sum as a Riemann sum and the upper Riemann sum as another Riemann sum. We're basically using virtually the same heights as we did before, except we're taking the infimum over the open interval, not the closed interval. Okay. And if I do that, and if I define the the slightly modified upper and lower Riemann integrals in basically the same way, so get some light in here. Okay, it's a lot better. Yeah, so if I define these slightly modified lower Riemann integrals and upper Riemann integrals in this following way, then it's annoying but not too bad homework problem that, well, it's not going to change this number here. So this upper Riemann integral is the same thing as this modified upper Riemann integral. And the same thing for the lower Riemann integrals. This lower Riemann integral is equal to this modified lower Riemann integral. So what basically allows you to prove this is that f, we're assuming, is bounded. Okay, And so this also tells us that because these two are equal and these two are equal, L prime of f is always less than or equal to U prime of f. Because I mentioned this is homework, that L of f is less than or equal to U of f. Okay, and this also means we can reformulate Riemann integrability in terms of these slightly modified upper and lower Riemann integrals. Particularly f is Riemann integrable if these two are equal, and if they are equal, we denote this common number as the area under the curve, as it should be. Okay, so what I want to talk about is I basically want to reformulate Riemann integrability in terms of or I want to take a more adult approach to the Riemann integral, and that's through step functions. Right? So yeah, we've already dealt with simple functions, and we've explained clearly how useful they are in measure theory and theory of Lebesgue measure. So step functions are kind of like the less mature version of simple functions for Riemann integrals. Particularly, what is a step function? Well, we've all seen step functions before. Basically, they're just functions on a closed interval that are constant on open intervals of my a to b, where these open intervals are, partition intervals. Okay? So the point here is that we're not specifying what this function is on these partition points. We generally don't care. There's something, because each of these partition points are an a to b, so psi is well defined on each of these partition points, but we don't really care what they are. Okay, so basically a trivial observation is that for a step function, if I define little mi prime and big mi prime as I just had a minute ago, so it's the infimum, little mi prime is the infimum of this function on this interval. Big mi prime is the infimum of psi on this interval, xi minus 1 to xi. Then trivially we have this equality here because, well, this function psi is ci on this interval. So clearly the infimum of this function is ci on this interval. Same thing, the supremum is clearly ci on this interval because the function is constant. It's ci on this interval, this open interval. Okay. So what does that mean? Well, by definition of the modified lower and upper Riemann sum, it's going to be this common sum here. Because, well, the definition I had a minute ago was the same thing as this, but instead of ci, I had little mi prime, but that is ci. The definition of the modified upper Riemann sum is basically this sum, except instead of ci, I have mi prime, but mi prime is ci. So these two are equal, and I claim that's enough to carefully prove that step functions are Riemann integrable, using what we've discussed previously. Why is that true? Well, this upper modified Riemann integral is the infimum of all these upper Riemann sums, these modified upper Riemann sums. In particular, the infimum is a lower bound for this particular modified Riemann sum, corresponding to this function, step function, and this partition associated to the step function. So we just showed that these are equal. It's this sum here. And this lower Riemann integral, this slightly modified lower Riemann integral, is the supremum of all these modified lower Riemann sums. So as a supremum, it's an upper bound. So this quantity here, this upper Riemann integral is bigger or equal to the specific upper Riemann sum, modified upper Riemann sum. As I mentioned, these two, well, L prime of psi, the upper Riemann integral, is less than or equal to the lower Riemann integral. The modified lower Riemann integral is less than or equal to the upper modified Riemann integral. Okay, so you'll notice that all of these quantities here are sandwiched between the same number. So that trivially forces, well, everything to be equal here. So in particular, these two are in fact equal. And they equal this common sum here because they equal both of these. So to summarize, a step function is Riemann integrable. And if P is the partition associated to my step function, sorry, this should be psi here. This should be psi here, and this should be psi here. So this should be psi here and psi here. Then if P is the if P is the partition associated to this step function, then this lower modified Riemann sum is equal to this upper modified Riemann sum, which equals the area under the curve of the step function, as it should be. Okay. So let's just review all this graphically. So just write down a example of a step function. Yeah, so this function here is C1 on x0 to x1. It's C2 on x1 to x2. It's C3 on x2 to x3. It's C4 on x3 to x4. Okay. When I say that, I mean on these open intervals. It could do a number of different things on the endpoints. We don't really care. Okay. And you'll notice that the red area here, the sum of these red rectangles, the sum of the areas of these red rectangles, is exactly this sum here when n equals 4. Okay. Which is going to be this lower modified Riemann sum and this upper modified Riemann sum. Again, really should be psi here and here, not f. And so this is just saying what we have here is that the sum of these red areas is what we should call the area under the curve, which we do. The sum of these red areas is the Riemann integral of the step function. Okay, so I claim that I can reformulate the modified upper and lower Riemann integrals in terms of step functions. Namely, this modified lower Riemann integral is the supremum of all these integrals where we're looking at step functions that are less than or equal to f on a to b, meaning phi of x is less than or equal to f of x for all x in a to b. Okay. On the closed interval a to b. Okay. And I claim that the modified upper Riemann integral is going to be the infimum of all these integrals, where we're looking at step functions where this should be psi here. Should be this psi here, so not phi. Psi is bigger or equal to f on a to b. Again, that means psi of x is bigger or equal to f of x on a to b. All right, so I'm just going to prove this. I'll leave the fun of proving this for homework. So let's begin by looking at an arbitrary partition. So just say P is some arbitrary partition. Little mi be as before. So little mi is just the infimum of little f of x over the closed interval xi minus 1 to xi. All right, so I'm going to cook up this step function as follows. All right, and I'm cooking it up in this way to basically force it to be less than or equal to f of x for all x in the closed interval a to b. So I'm going to define it as little mi if x is in this half open, half closed interval corresponding to a partition P. And little mn if x is the right endpoint. So by definition of a partition, this basically handles everything in the closed, half open interval a to b, and this handles b. Okay, so we look at those two cases. Let's say little x is in this half closed, half open interval. Then it's in one of these half open, half closed partition intervals. By definition, phi of x is little mi. Little mi is the infimum of f of x over this closed interval, actually, xi minus 1 to xi closed. Certainly, if x is in this half closed, half open interval, then it's in the closed interval, where I put a bracket here. So that this infimum has a lower bound of all these f of x's is less than or equal to this particular f of x. Same thing happens if x equals b. If x equals b, phi of x is little mn. Little mn is the it's the infimum of my function on the closed interval xi minus 1 to xi. B is certainly in the closed interval. Little mn is the infimum of my function on the closed interval xn minus 1 to xn. Certainly, b, which is xn, is in the closed interval xn minus 1 to xn. It's the right endpoint of that closed interval. So the infimum is less than or equal to f of b. All right. Now, so what did we just do? Ignore this for a second. We just proved that for any x in the closed interval a to b, phi of x is less than or equal to f of x. All right, now, since phi of x is little mi on each of these open intervals, we have that the corresponding modified lower Riemann sum, by definition, is going to be this sum here. Or rather, not by definition, but what we shown a moment ago. So remember, we mentioned that essentially by definition, that if my step function is ci on this open interval, on each of these open intervals, then the modified lower Riemann sum and the modified upper Riemann sum coincide, corresponding to this partition, and it's just going to be this sum here. Okay. So on each of these partition intervals, phi of x is little mi. So particularly the lower modified Riemann sum is this sum here. We also mentioned, proved that this is going to coincide with the integral, the area under the step function. Okay. Well, remember star is the supremum of all these integrals. So the supremum is a upper bound for a particular one of these integrals. Integrals over step functions that are less than or equal to f on the interval closed interval a to b. So this proves that for any partition, star is bigger or equal to the modified lower Riemann sum. Remember, star is this supremum here. So now we take the supremum over all partitions. So the supremum, well, this is a upper bound for all these partitions. Supremum is the least upper bound. So the supremum as the least upper bound is less than or equal to star. Okay? And the punchline, basically, to summarize, is that given a partition of A to B, we can cook up a step function where the modified lower Riemann sum is the integral of the step function, which proves half of our assertion. The converse is pretty straightforward. Let's say I have a step function. So it's some ci, some number ci, on all of these partition intervals for some partition of A to B. Okay, and in star, we're taking the supremum over all these integrals, integrating step functions on A to B, where the step function is less than or equal to f on A to B. All right. So what does that mean? Well, if x is between xi minus 1 and xi, if x is in this open interval, then by definition ci is 5x. We're assuming 5x is less than or equal to f of x for any x in A to B. Certainly if we're in this open partition interval, we're in A to B. So, right. So for x in each of these partition intervals, ci is less than or equal to f of x. Well, that means ci is a lower bound for f of x on this open interval. The infimum is the greatest lower bound of, the infimum is the greatest lower bound for f of x on each of these intervals. So the greatest lower bound is bigger or equal to this specific lower bound. So mi prime is bigger or equal to ci. And what does that mean? Well, the Riemann integral of 5x, again, is just ci, the sum of ci xi minus 1. Ci is less than or equal to mi prime. And this is the modified lower Riemann sum corresponding to this partition. Okay. But remember, the lower Riemann integral is the supremum of all such lower Riemann sums. So this specific lower Riemann sum is less than or equal to the supremum. Supremum is an upper bound. Okay, so we play the same game here. Star is the supremum of all these integrals, integrating step functions that are less than or equal to f on A to B. So, right, the supremum is the least upper bound of all these integrals. This is an upper bound, sorry, the supremum is the least upper bound for all these integrals. This is an upper bound for all these integrals. So the supremum is less than or equal to this lower bound. And so that proves that star equals the lower modified Riemann integral.